I'm going to detail 90 mastering terms, and it's going to be crazy. This is an epic video, so make sure you have a coffee, a snack, a pen, notebook, smash the subscribe button, like the video, and let's get started. Mastering engineers work with sound, the disturbance of atmospheric pressure in molecules, like the ones between your headphones or speakers and your ears, or my voice and this microphone's diaphragm. This microphone's diaphragm converts these changes in pressure to an alternating current that is directly proportionate to the displacement of molecules from their equilibrium position and the duration of that displacement over time. This is visually represented as a waveform. A waveform graphs the changes in sound over time. The y-axis of the waveform represents the amplitude, while the x-axis plots frequency. The sound which waveforms make up are complex in their nature. A sinusoidal waveform, otherwise known as a sine wave, represents a single frequency and amplitude uniform across time. Now, that isn't how sound propagates in real life. The sounds we hear every day are complex in their arrangement, so let's break down the makeup of sound. All sound contains a fundamental frequency. The fundamental frequency is the lowest cycling pressure and most often the strongest within a sound wave. Built upon this fundamental frequency are a series of harmonics. Harmonics are additional frequency waves which are multiples of the fundamental frequency. Each higher multiple is typically softer in amplitude than the previous one. Also, not all harmonics and fundamentals sit at a constant sound pressure. Sound varies in pressure by 4 characteristics: the attack, decay, sustain, and release. The attack of a waveform is the initial peak and directly correlates with the instantaneous particle displacement in atmospheric pressure within a sound wave. The decay and sustain dictate how we perceive the loudness difference between that initial particle displacement, or the peak, and the average of amplitude that displaces over a given time, or the loudness. The release is the time it takes from that disturbance of atmospheric pressure to return to an equilibrium. The way fundamental frequencies, harmonics, and the quality of each one's attack, decay, sustain, and release interact with and converge with one another affects the characteristics of each and every sound we hear. As mastering engineers, we identify, measure, and quantify the following qualities of a waveform by the following means. We identify the transient quality of a waveform's playback as the difference in amplitude and tone between the attack and the decay of a waveform. These transients make up the microdynamic qualities of the material, and that references the short-term variations in dynamics between transients which denote rhythm, articulation, and bounce in a mix. The peak is the single loudest point of the waveform, and we measure that in 2 methods. A measurement of decibels full scale measures the sample peak, whereas a measurement of decibels true peak measures the loudest intersample peak between sample values. This can be shown via an offset sync waveform, whereby the sample peak is lower than the true peak of the signal. True peaks are measured via the standard set out in ITU BS 1770, where a reading error between decibels full scale and decibels true peak of a 48 kHz file can be several decibels. But by oversampling, these discrepancies in the measurements can minimize down to tenths of a decibel. Oversampling is the process of interpolating new samples between the existing sample points for a more accurate read. We also measure and read waveforms via LKFS, or loudness K-weighted full scale, or LUFS, which allows us to quantify the overall strength of a signal relative to how the human ear perceives tonality. This is calculated by a signal which is filtered with a 4 decibel high shelf from 1 kHz and above, in a series with a second order high pass filter with a corner frequency at 100 Hz. The RMS, or root mean squared, of this signal across a 400 millisecond block is calculated. Root mean squared values are calculated by taking the amplitude value of each sample point across a given window, squaring each value, averaging the values, then taking the square root of those values average. This RMS calculation of the filtered K-weight signal is taken every 100 milliseconds to create a 75% overlap in the readings. These windows of calculations contribute to a running average, but values below -70 LUFS and values which are 10 LUFS below the current average are discarded from that running tally. The resulting running average provides us with a measurement of approximate perceived loudness, which we use to create windows to read the following. Long-term integrated loudness is the loudness of the overall program material. Short-term loudness is the running loudness of the material at 3-second intervals. Maximum short-term loudness is the loudest 3-second window throughout the whole of the material. Momentary loudness is the loudness of one 400 millisecond block window. Crest factor is the difference between the peak value and the long-term integrated loudness, describing the dynamic characteristics of the waveform. Moving into digital audio, the alternating currents which these waveforms represent are received by an analog to digital converter. Analog to digital converters convert the alternating current to digital numbers by stabilizing the incoming signal to a non-changing voltage by a sample and hold circuit controlled by clocking. These time-bound, non-changing voltages feed a series of comparators arranged between resistors, providing 6 decibel steps in a series where the output is either fully positive or fully negative to signal binary zeros and ones to a digital circuit that stores this data via the method of pulse code modulation, or PCM for short. PCM stores this stream of data as the amplitude of the signal at uniform intervals quantized to the digital range of steps. The uniform intervals are dictated by a given sample rate. The sample rate dictates the clocking's regular time-bound intervals of samples which are captured and stored. Typically, rates of 44,100 samples per second are standard for CDs, or 48,000 kHz for capturing and recording, but can go up to 88.1 kHz, 96 kHz, 192 kHz, and higher. Nyquist theory shows us that the highest frequency allowable in a digital waveform is equal to half of the available bandwidth. With a bandwidth of 44,100 samples, the highest allowable frequency this sample rate can store is 22,500 kHz, which sits outside the upper limits of human hearing. So, the digital audio can represent all audible information that can be perceived by a human. A fun fact, the earliest form of Nyquist theorem was established in 1925 by Harry Nyquist when looking at the fastest rates at which telegraph lines could transmit Morse code, when he proved that the fastest pulse rate allowable was half the available bandwidth of the telegraph line. Digital range of steps in PCM, or pulse code modulation, have a range dictated by the bit depth. Bit depth provides the available range of numbers to store digitized data samples, 2 to the power of the bit depth. The larger the numeric range, the greater the distance and resolution between the peak and the noise floor. 8-bit has 256 available numbers ranging from -127 to a +128 with a noise floor of -48 decibels full scale. 16-bit has 65,536 available numbers ranging from approximately -32,000 to +32,000 with a noise floor of -96 decibels full scale. And 24-bit has 16.7 million numbers ranging from -8.38 million to +8.38 million with a noise floor of 144 decibels full scale. 32-bit float, the range is so large, let's not go there, but in practical terms, CD consumer audio using the REDBOOK standard of 16 bits at the previously mentioned 44.1 kHz sample rate. And 24 bits is typically used for most production purposes in digital formats. Most stores, however, internally operate at 32-bit float, providing headroom for overs. This is why I always suggest to export mixes at 32-bit float, as if you have a few sneaky peaks that go over -0 decibels full scale, that 8 extra bits of float is forgiving that the data will be stored and won't be hard-clipped going into the ceiling. The opposite of how bit depth affects the full-scale peak and resolution of a waveform is how changing the bit depth affects the lowest bits or the softest part of the waveform. This is done by truncation. Truncation is the process of discarding the lowest bits of information. Numerical values are rounded to the lowest integer value, which isn't a big issue with loud signals, as rounding a value of 200.9 down to 200 is only a read error of 0.45%. And when working at 24 bits, those high bit values are in the millions. So for all intensive purposes, it almost replicates to exact when you're going from 24 down to 16 and you have a loud signal. However, the lowest bits, truncating from a value of 1.9 down to 1, is an error of 90% and results in an audible effect on the softest passages or tails of a sustain into the noise floor, and this is otherwise described as truncation distortion. Dither is a very soft noise added to a signal to avoid the audible effects of truncation distortion when reducing bit depth. Dither achieves this by adding a very soft noise at equal volume to the lowest bit. Adding dither noise assigns a random value to the lowest bit, which minimizes these rounding errors that cause truncation distortion. This dither noise is also less noticeable or audible relative to the truncation distortion that otherwise would be introduced. Now, these streams of pulse code modulation are programmed by a codec. A codec provides an algorithm for encoding and decoding the digital stream. Common lossless audio codecs like WAV, waveform audio file format, or AIFF, audio interchange audio format, retain all of the PCM sample rate and bit depth data. Lossy audio codecs like MP3 or AAC advanced audio coding compress the data stream by discarding parts of the data and making inexact approximations to represent the original stream. This creates its own bit stream of data whereby the bit rate determines the resolution of the data kept. A stereo lossless WAV file with 48 kHz sample rate and 24 bits per left and right channel provides a bit rate of 3072 kilobits a second. MP3 and AAC algorithms are designed to encode data up to 320 kilobits a second, almost 10 times lower than that of lossless 48 24-bit recording. For perspective though, Spotify's normal streaming bitrate is 96 kilobits per second for normal mode, and Premium allows for very high quality at 320 kilobits per second. Apple's initiative, Apple Digital Masters, formerly MFIT or Mastered for iTunes, is a set of guidelines and protocols outlined by Apple, which mastering engineers on their providers list adhere to achieve the best quality when encoding to AAC formats. As someone on that providers list to adhere to their guidelines and protocols, here's the process for authoring an ADM master I use. I ensure clients provide an appropriate premaster. A premaster is a lossless digital audio file of an approved mix by a client, which is delivered to the mastering engineer for mastering. Typically, that's done at the native sample rate and bit depth of the mixing session. I then quality control it to make sure there are no digital overs or clipping. I monitor my session with a peak meter to ensure at no stage between processes the signal exceeds 0 decibels full scale. I ensure my final limiter is set to -1 decibels true peak. And then I export signed off masters at the native sample rate and bit depth from the session of the original mix, void of any sample rate conversion or changes from the source material. And then I audition all prints of the masters through Apple's AAC codec to ensure that it's translating well. Another format for delivery of masters are DDPIs, Disk Description Protocol images, which is a digital image containing the data of an image of a CD. That's used by replication plans to produce CDs from. The DDP image contains 5 files: an audio image file, a DDP identifier, a DDP stream descriptor, a CD text bin, which contains the track titles, timing, and metadata, and a subcode descriptor. Now, whilst the DDPi carries the metadata information in a separate file within the image, metadata for the aforementioned codecs live within the encoded audio files. MP3s use an ID3 container, and to date, ID3 v2.4 can carry 83 frames of metadata. AIFF natively support 5 chunks. Each of these chunks are 4 bytes or 32 bits for name, author, comment, annotation, and copyright, and another open chunk for assigning ID3 metadata. WAV files have an info chunk which can be used to embed any kind of metadata, including ID3 metadata, but that isn't standardized. What is standardized is the embedding of ISRC metadata via the EBU Tech 3352 guidelines using the info chunk. An ISRC, or International Standard Recording Code, is a unique and permanent identifier for a specific recording which can be permanently encoded onto a product as its digital fingerprint. It's embedded onto master files during mastering or integrated into a publisher's library data when submitted through an aggregator. The first 2 characters dictate the country code, the next 3 letters are the registering code, the next 2 digits are the year of reference, and the final 5 digits are the designation code. Digressing from sampling theory and digital audio, mastering engineers need to have a handle on audio qualities, namely identifying and quality controlling the introduction or presence of artifacts, which are unwanted or undesirable sonic material present in the sound production of a mix. This includes identifying dropouts from incorrect edits. This often happens when a region of audio is cut short, causing the unexpected absence of a sound source in a mix, or when 2 audio regions are compiled together incorrectly without using a crossfade. Now that causes a click between the 2 regions because the waveform mid-cycle has been cut before returning to unity. A crossfade prevents this by summing the signals together with opposing fade directions, where the clip preceding the phase will fade down to the noise floor while the next clip will fade up from the noise floor in tandem with one another. Buzz, hum, hiss, or crackles are forms of noise that can be introduced by noisy equipment, faulty equipment, or improper gain staging techniques in the recording process. As this passes forward through mixing stages, it's an important aspect of quality control to mitigate and manage these artifacts. and this also includes anything that passes through the mixing stages and is present during mastering. It's an important part of mastering quality control to ensure none of those get through to the final print. Intermittent noises such as ticks, clicks, or pops can be produced for the aforementioned, but also come from common mouth noises like lip smacks in a vocal take. Other vocal artifacts mastering engineers should be able to identify are the proximity effect that typically occurs in the recording of vocalists too close to a microphone, where there is a greater amount of sound pressure interacting behind the diaphragm, causing a shift in phase between the sound pressure being transduced at the front of the diaphragm and from behind, providing an artificial boost of low frequencies relative to that difference in phase. This proximity effect also feeds into the presence we detect in plosives, which are sounds that force out a high velocity of air or pressure, typically produced by consonants that use the tongue tip, T or D, the tongue body, K or G, or the lips, P and B. In opposition to plosives is sibilance. Sibilance occurs on consonants made when directing a stream of air with the tongue towards the teeth. Sounds like S, Z, which produce high sound pressures at high frequencies. This is namely not pleasant as microphones exacerbate these effects, and whilst in mixing, engineers will aim to minimize the effects of sibilance. However, long periods spent working on a mix can often lead to the acclimatization of those frequencies in our ears, and it's our job as mastering engineers to make sure we pick them up for correction before they get printed onto the final record. On all live recorded material, depending on the method of capture, positioning of the microphone, and the sound, the room's modal resonances or ringing can present itself on recorded material. All rooms have resonant frequencies. Each room resonances are dictated by the 3 dimensions of the room's lengths, which are directly proportional to half wavelengths which double upon themselves and ring out, as well as the materials which make up the room. Other artifacts like unwanted digital clipping. Digital clipping tends to be harsh and, unless blended in as a production element or sound design effect, tends to be unwanted on the final material. Finally, the ability to identify various distortions, which is the introduction of an additional sound source not present in the original signal. Harmonic distortion. We discussed naturally occurring harmonics in sound waves at the start, and like those, harmonic distortion comes from processes used to manipulate the sound source or signal by introducing harmonics relative to that fundamental signal. There's also aliasing distortion, which is a form of inharmonic distortion produced by processes which introduce harmonic distortion outside the bandwidth of a sample rate's NYQUIST frequency, whereby the sample rate can't produce the harmonics above its NYQUIST frequency. Instead, it folds these harmonics down from the NYQUIST frequency and they remain inharmonic to the nature of the original material. Intermodulation distortion is a form of inharmonic distortion produced in processes by the introduction of new frequencies from the sum difference of present frequencies in a signal. When identified, these artifacts are managed in 2 manners by a mastering engineer: flagging the artifacts with the mixing engineer for rectification ahead of mastering, or by using audio restoration software. Audio restoration software like iZotope RX Suite uses complex DSP, digital signal processing algorithms, to manipulate the audio in a manner which minimizes or completely removes the audibility of these artifacts. More common forms of digital signal processing mastering engineers utilize are equalization filters and dynamic processors. Equalization filters can be used to selectively pass, attenuate, or boost a specific set of frequencies in a signal. There are 3 types of filter categories that allow us to do this: high and low pass filters pass frequencies above or below a specified frequency. Shelving filters boost or attenuate the gain above or below a specified frequency. And band pass filters, which passes frequencies within a surrounding range of frequencies. High and low pass filters operate by having a specified cutoff frequency and slope. The specified cutoff frequency is also known as the half power point, as the frequency response has fallen by 3 decibels at the cutoff. After the cutoff point, the specified slope continues to attenuate the signal. Pass filter slopes are inherently in multiples of 6 decibels per octave. A 6 decibel slope is known as the first order pass filter, as a filter made from a single capacitor in an analog circuit provides a fall-off rate of 6 decibels per octave. Any additional multiples of this, second order, third order, requires a multiple of these filters in a series, hence a second order being 12 decibels, third order being 18 decibels of slope. Shelving filters like a high shelf or low shelf operate similarly. But rather than having a constant rate of attenuation towards cutting out frequencies below or above a cutoff frequency, they boost or cut to a specified amount of gain. Now, bandpass filters are used in the construction of commonly used barrel filters. Barrel filters have a center frequency rather than a cutoff frequency, whereby a Q value or quality factor is used as a parameter to determine the bandwidth of frequencies affected around the center frequency. The lower the Q value, the wider the bandwidth. The higher the Q value, the narrower the bandwidth. The center frequency and the Q value paired with a specified amount of gain, positive or negative, allow the engineer to boost or attenuate this band of frequencies. Other useful filters mastering engineers use are band stop filters, otherwise known as notch filters, which allow all frequencies to pass except those within a range of the center frequency. This is a common filter for removing resonant frequencies or ringing from a material, as well as tilt filters, which make an equal amount of boost and attenuation on opposite sides of the center frequencies. Dynamic processes are processes which, instead of affecting the frequency response of audio, affect the dynamics or the loudness and amplitude of audio. A compressor is the most common form of dynamic processor used in mastering, whereby a threshold is set. Any signal passing above that threshold will be attenuated by a given ratio, which dictates how much volume to automatically reduce. The time it takes to arrive at that full amount of attenuation is dictated by the attack time, and the time it takes for the signal to return to unity gain is dictated by the release time. Another form of compressor used is a multiband compressor, whereby a signal is split using a series of pass filters to create separate bands of audio which can be manipulated in volume independently of one another. Or a dynamic EQ, whereby a single band pass filter is manipulated in parallel with a signal and resummed to produce an EQ filter that is power or amplitude dependent. The next type of dynamic processor used in mastering is a limiter. A limiter has an infinite ratio, whereby it will completely prevent any signal from exceeding the threshold in amplitude. Limiters are used to buy headroom and raise the overall level of program material. Headroom is the amount of distance between the peak value of a waveform and the maximum available bandwidth of the given bit depth, otherwise denoted as 0 decibels full scale. Limiters commonly feature two other parameters: look ahead, which allows the peak detection circuit to read the incoming signal with an offset to anticipate loud peaks before they happen, and true peak limiting. True peak limiting allows the control signal to monitor a signal with interpolated sample values for more accurate reading and prevent underreads on the detection circuit and overshoots at the limiter's end. A mastering engineer's end goal is to take a mix and prepare a production master ready for dissemination. During that process, the knowledge of aforementioned terms are critical, as when preparing a production master, an engineer needs to take into consideration tonal balance, dynamic composition, and translation of the material on consumer systems. Tonal balance is particularly critical. The human ear is very nuanced in the way it perceives and interprets sound relative to frequencies. This is objectively detailed in the Fletcher-Munson curve, which plots how the human ear perceives different frequencies at different volumes. Whilst we're not aiming to match a curve in frequency response when manipulating a signal, being empathetic to the nuances of how we perceive higher frequencies in opposition to lower frequencies help us make educated choices on how we manipulate the tone of a final production master. Another aspect of manipulating tonal balance is for how the material will translate on consumer systems. Room modes, low frequency, hum, or an excess of low end will be exacerbated on consumer systems that use subwoofers, whereas sibilance, digital clipping, and artifacts will be exacerbated on smaller consumer systems like iPhone speakers, laptop speakers, or in-ear headphones that have naturally more upper mid presence. Finally, mastering engineers consider dynamic composition with both musical and technical sensibilities. Musically, we utilize dynamic processes to embellish movement, rhythmic motive, or detail and articulation in a piece of music. Technically, we utilize dynamic processes to manage the dynamic range or CREST factor and provide us with the necessary headroom to increase the overall loudness of the program material. I hope you've enjoyed this A to Z terms list and explanations. I'll be doing more of these for other aspects of mixing, mastering, and productions in the future, so don't forget to smash the like button and subscribe for more.